So let us do the simulation for the tuned amplifier through the Multisim software. Before go through the simulation, let us have some sort of discussion on the tuned amplifier. Tuned amplifier will be classified into two types: a small signal tuned amplifier which are operated in the class A mode, and large signal tuned amplifier which are operated in the class B, class C, class AB mode. And small signal class A type of tuned amplifier will be under three categories. Will be classified into three: single tuned amplifier and double tuned amplifier, stagger tuned amplifier. So now in this session we'll try to do the simulation for the three amplifiers over here. The single tune will be having a circuit diagram like this, and double tune of this one, and a stagger tune of this one. We'll try to do the simulation one by one. And before you do the simulation once again, let us compare this kind of CE amplifier which you already designed in the last semester, and with respect to CE amplifier, and how the single tune amplifier will be having a different properties in terms of the frequency response is. So as we know, the transistor is connected with the RC and RE bypass capacitor, and input is given through the base terminal and taken across the output across the collector terminal. So once you do the frequency response and simulation for AC analysis, if you do it, the frequency response curve will be like this. Frequency response will be flat. The frequency response curve will be like this. Frequency response will be flat for the wide range of frequencies. So this is x-axis is frequency and y-axis is my gain. So when like the frequency response is flat over here for this range of frequencies, right, all the frequencies are amplified equally well. So for the 20 Hz to 20 kHz for suppose, for all the frequencies are like equally amplified, but where in the radio receivers what I need is a selective frequency components itself need to be amplified, and rest of the frequencies need to be attenuated. Other stations should not be amplified. So where that I wanted to get like a frequency response not like this, so where I will be expecting the frequency response with respect to frequency, I will be expecting that maximum gain only at one frequency. At only one frequency I will be expecting the maximum gain, and rest of the frequencies over here and over here should be attenuated. So I have to get a poor response across the other frequencies. Only at the frequency we call it as a center frequency or resonant frequency itself, I should get like a maximum gain. So for that kind of requirement, I have to design a single tuned amplifier. So the modification with respect to this is my CE amplifier. CE amplifier. The modification with respect to CE amplifier is where I have like a RC network. What I do is I have to remove that RC network. In place of RC network, I will be keeping a frequency response element, frequency reactive components here. Why frequency reactive components I have to keep here is, so when that I'm expecting that only selected frequencies itself I have to get a maximum gain. So that particular circuit, when that particular resonant frequency comes, that particular circuit over here, that resistance of the particular module should be very high. So that is possible only with the tank circuit which I'm trying to make it. So this tank circuit will be offering that maximum impedance at resonant frequency FR. So at resonant frequency FR, what happening is, if it is a tank circuit, if it is considered the capacitor and the inductor, if I keep it, what the tank circuit will behave is, how it behave is, at resonant frequency F is equal to FR, X is equal to XL, X is equal to XL. So what happening, if you solve this one at resonant frequency, we'll be getting a formula like a 1 by 2 pi root LC. So at that particular frequency, under the resonant frequency, the tank circuit will be under the resonance. The capacitor will be taking that entire energy from the inductor, and the inductor will be taking the entire energy from the capacitor itself. So it means that energy is transferred between these two components, that whatever the external current from the VCC, it will take the current of this one is around 0. When the current is 0, it means that the particular entire circuit is like an open circuit. It is like open circuit, offering that impedance is maximum. When the impedance is maximum, as we know, the gain of the circuit is totally depending upon the ratio of these two. As that gain of the circuit is, as the resistance of the circuit, impedance of the circuit is increased, automatically gain will be increased. So only at the center frequency itself, the gain will be the maximum. So that kind of that frequency reactive components like a capacitor and inductor, that kind of tank circuit, when I'm keeping across this one only, it is possible. So that's why I keep like a transistor circuit along with the tank circuit as a load, a tuned circuit over here as a load, and I'm keeping and I'm replacing that circuit and I'm trying to do the simulation. So coming to the circuit diagram over here in the circuit diagram in the multisim. So as we know, the transistor virtual we took it, C amplifier case, how we done the simulation the same way, like I have to do the simulation, I have to do the connections also in the same way. The emitter resistance and bypass capacitor and R1, R2 coupling capacitor and input is everything is same. Only the thing RC, which I keep it around 2.2 kilo ohms, is replaced with the tank circuit. So where that capacitor in the one branch and inductor in the another branch, along with that small resistance I'm keeping. So it's around like 100 ohms I'm keeping. 100 ohms I'm keeping. So with the resistance, right, I can completely say that the inductor with some losses. So because like that pure inductor will be practically not available. It's not practically like inductance will have some kind of losses, eddy current losses, and that and all will be represented with some kind of resistance over here. That losses will be represented by this resistance. So this is a capacitor, and this is what my losses with inductor, right? So this tank circuit is connected over here, and let me do the simulation for this circuit. So for the simulation, what I'm trying to do is I will be keeping my inductance value as parameter, and I will be changing my inductance as we already discussed. That resonant frequency is nothing but 1 by 2 by root LC. What L value we kept it here and what C value we kept it here. With that we have to calculate the resonant frequency, and also we have to observe that frequency response that at only that resonant frequency itself that maximum gain should come. So let us see that is it possible like that or not. So what I'm trying to do is I will be going with analysis type, analysis type, analysis type. And before go with the analysis type, one thing let me tell. So I have to make sure that the branch over here, it should be like a double click on that once, and we have to give the name of this one is output one. Otherwise, like we have confusion when we select that output while we do the simulation. So that before you have to give that double click on the particular branch and you give the preferred name as output one and give OK. So now when I go with selecting a simulation type, I have to go with the parameters view because like I'm changing the inductance value of this one for multiple times. So by changing the inductance value, how the frequency response is getting varied, that's what I wanted to verify. So in exactly like how I have the circuit C, how that waveform that I'm expecting is. So inductance value, what I do is I will be keeping the inductance value like 1 milli once, and I will be changing to 3 milli and changing to 5 milli. So here the inductance value, which is like initially at 1 milli, right, what I'm trying to do is I will be using a parameter sweep for the 1 milli to 5 milli, and I'm expecting that a formula I have it over here. This is 1 milli. When I keep a 1 milli with a capacitance value of 0.01 micro, so that resonant frequency for this one is 50 kilohertz, right? You can see the formula 1 by 2 pi root square root of this one into this one. So will that we'll get a resonant frequency of 159 kilohertz. And when you keep like 1 millihenry, you will be getting 159 kilohertz. So in the same way, when I go with the sweep parameter of 3 milli, I will be getting a resonant frequency of 91 kilohertz. As that inductance value increases, resonant frequency will be decreased. So we have to verify the same thing. As the inductance value increases from 1 to 3, 3 to 5, so I have to get the resonant frequency from 159 kilohertz to 71 kilohertz. So let me show the same simulation over here in the multisim also. So what I'm trying to do, the parameter sweep, I'm like using the analysis type. The device name is inductor, and let me know that which inductance, like L1 is inductance value, that L1 is the name of the inductor. So we have to select like L1 is the name of the inductor, and the parameter which I'm trying to change is the inductance value. So like initially it is 1 milli, now I'm trying to change from 1 milli to 5 milli, 1 milli to 5 milli, stop value is the 5 milli. Yes. So here how many times I'm trying to change it? So number of points I'm trying to make it as a 3. So it means, so there are like 3 times of simulation will be performed from 1 to 5. It means for every increment of 2, right, from 1 to 2 increment it will be like 1, it becomes like 3. Again 2 increment, it becomes like 5. So 1, 3, 5. At 3 times it will be doing the simulation, right? So what kind of simulation it has to perform is AC sweep simulation I have to perform. So I have to click on this one, and output type, we have to select the output type. So output type is like I have 3 outputs, output 1 and output 2 and output 3. So let me remove that output 2 which is there, because I am not doing the simulation for the output 2, I am doing the simulation for the output 1. So what I do is I will be selecting my output 1, very good, output 1, add, add, and then run. This is how, this is the magnitude plot, this is the phase plot. So like let me remove that, select it and give the delete, so that the particular plot is getting deleted. So we can see that the frequency response plot will be like this. Once we go with the cursors, you can select the cursors here, and you can go to that particular frequency. Here this is the frequency. You can see that 159 is the kilohertz frequency, right? 159 kilohertz frequency at which we get a peak. The same peak we are expecting also, 159 kilohertz at which like we are expecting a resonant frequency. That particular peak should be appeared across this one. So only the selective frequency of 159 kilohertz itself, it will be amplified by the tuned circuit, a tuned amplifier, when I give like a value is 1 milli. For suppose like I wanted to tune to the particular frequency of 91 kilohertz. For that what I do, I have to tune that inductance value to 3 milli. So here that case also simulated here, and we can see that when I go with that frequency, this is the case. Here you can see this is the case, right? This color, right? So when I keep like a 3 millihenry, so 3 millihenry, so that particular inductance value, what happening, that frequency response is appeared over here with a frequency of 91. So like that, if I go with the third case, when you have that inductance value is around 5 millihenry, so I can get that frequency response which will be appeared across this one. So it is around like 71 kilohertz, like that. Wherever like you want the frequency response, like for certain frequency of the signals you wanted to allow. So your frequency of the like signal, let us suppose radio which or some other frequency signals we wanted to allow. So we have to know that at what frequency that radio which is signal, like the particular songs are played. So at that frequency we have to select it over here, and we have to tune to that particular frequency. For that we have that option that the inductance value can be adjusted. So that's why what we do is that inductance will be like a adjustable inductance, we'll keep it. So that adjustable inductance of 1 milli to 5 milli, so that I will be getting a different selected frequencies are amplified. And now if you observe the three curves once, all three curves are not in the similar way. I can observe one thing: this will be having more selectivity, has more gain, and a very narrow band. So only selected frequency will be amplified. So, but in this case, it is not happening so. So it is the reason, right? I can show you one simulation over here. This is what I will provide the link for the simulation, right, in the description. After you go through the link, you have the circuit options and go with the symbol circuit and select a band pass filter. So once you select the band pass filter, you can see that options over here. What kind of tank circuit we have? The same tank circuit is connected over here. This is considered as a band pass filter. So now here the Q factor of the particular tank circuit decides that so the selected frequencies will be in what format or in what way, like it will be amplified. So if the Q factor of that circuit is very less, this is the Q factor of the circuit is less, so we can see that the wide range of frequencies are like almost equally amplified well. So from this one to this one is not having a proper selectivity, so other frequencies also it will be amplified, right? So when we need a more selectivity, where I need like a very narrow bandwidth, for that I have to adjust the circuit such that the adjustment will be done automatically, but we have an option that the Q factor can be adjusted through the simulation. So Q factor, once I increase, you can see that the frequency response, this one you can see it here. So once the Q factor increases, the selectivity of the circuit is increased. So Q factor increases, the selectivity of the circuit increases. So it's our requirement. Few tuned amplifiers will be needed with the maximum selectivity. So for that we should know that how to increase the Q factor for the tank circuit. It's almost depending upon the Q factor of the tank circuit. So here if you see that if you have parallel resonant frequencies, so if you see that the capacitor and inductor plus resistor, this tank circuit, if you calculate that Q factor for that one is omega L by RS, the series resistance. Series resistance is nothing but the resistance of losses of the Butler inductor. So we need to make sure that the Butler inductance should be it shows the energy with respect to losses, right? So here the losses of the inductor should be as minimum as possible. For that, what I have to do is I have to make sure that resistance value should be as minimum as possible. Resistor is nothing but the indication of the losses, correct? So I have to make sure the resistance of the Butler tank circuit should be as minimum as possible, so that losses will be as minimum as possible. So the energy stored across the inductance will be as maximum as possible. So that is what happening here. The quality factor that is nothing but the L value by RS value. So L value, if it is maximum, automatically the Q factor of the Butler tank circuit also maximum. So here also what happening is in our simulation, so in the three cases what we are trying to do is, so with respect to the resistance value, the inductance value is increased. So in the first case the inductance value is 1 milli, in the second case the inductance value is 3 milli. So like that, if I increase the inductance value, the quality factor of the tank circuit is also increased. As the quality factor increases, the selectivity of the circuit also increased. So as we can see this one, so as quality factor increases, that selectivity is increased. So the same thing happening here also. So in the simulation we can see that the same thing happening here also. The selectivity of the Butler tank circuit is increased as the inductance value of that circuit is increased. So here that inductance value is increased. Delete. As that inductance value is increased, so this is the case for that 1 milli, this is the case for 3 milli, this is the case for 5 milli. So more selectivity, more quality factor, or more inductance, that all three are parallelly happening. Yes, so that is the first case where we are trying to do the simulation for the single tone amplifier. And one more point like I wanted to show you is, after we do the simulation, you wanted to make sure that the particular simulation results need more clarity. For that, there is an option is provided in the Multisim is you can go with the right export option, like that entire data of this one is converted into the Excel format, right? Delete this one. Excel format, we can convert into the Excel format. So you click on this one, give OK. After that, so all the points, traces of the particular waveform, it will be visible on a Excel sheet. So you can see the Excel sheet over here. That this is the Excel sheet now it is created. So you can do it. You can select this one and go with the insert. And there is option like you select it. So whatever that waveform that visible, that same waveform you can recreate it over here through the Excel sheet also. So here you can change like a different formats, and so that you can size that the particular all the curve, and you can rename it, and you can do that all the modifications across the Excel sheet. So after finally, this is the diagram, right? We got it through the Excel sheet itself, and whatever that waveform that we got it in that particular format is created into the Excel sheet. That Excel sheet information is now created as a plot, right? So this is the first case. We have done the simulation for the single tuned amplifier, and now coming to the second case where the double tuned amplifier. So the same kind of tank circuit I'm keeping it for 2 times. So for that what I'm doing is I will be keeping a inductor for the first circuit and inductor for the second circuit, which is connected as a transformer. So we have to know how the transformer is connected. We have to click that components, and here we have a transformer and a coupled inductor transformer. We have to select it and give OK. So that transformer we have to connect it over here, and that particular transformer primary coil is connected with the first capacitor and the secondary coil is connected with the second capacitor. So that is how like I will be making a tank circuit for two times. So this is considered as the first tank circuit, this is considered as the second tank circuit. So when we have multiple tank circuits, we call this one as a two tank circuits. This one is called a double tune amplifier. And from this one we select this port as output port and giving the notation of output 2 and give OK. So now let us do the simulation for the tank circuit. Let us do the simulation for the double tune amplifier right now. While we are doing the simulation, we have to remember one thing. So if you give the double click on this one, there you can see that primary coil inductance is 1 milli. So whatever that 1 milli I kept it, that same 1 milli I am taking it here. And the secondary coil also taken with the 1 milli. And the coefficient of the coupling is very important here. That coefficient of the coupling initially is given with the 0.1. So now what I am trying to do is I will be doing the parametric sweep for this one also. The inductance value is taken as a parametric sweep, and now what I am trying to do is that coupling coefficient is taken as a parameter sweep parameter now. So give double click on this one. I select a parameter sweep once again. So previously inductance is the value, I take it a parameter sweep. Inductance value taken as a parameter sweep. So now mutual inductance is like transformer, right? I have to select a K value. K value is nothing but a mutual coefficient, inductance coefficient, coupling coefficient. So initially I've shown you that the present value of the K value is given as 0.1. So now what I'm trying to do is 0.1 is nothing but 100 milli. So what I'm trying to do is I will be keeping it is from the 0.0012 100 milli, right? 0.0012 100 milli, right? So I consider this one is very loose coupling, this one is like a very tight coupling. So here I can show you, right? We are expecting this kind of frequency response for the double tuned amplifier, where at a double tuned amplifier what happening is, so they based on that type of the coupling. If it is loose coupled, that frequency response at center. If it is tight coupling, so the frequency response curves at two resonant frequencies will be getting two peaks, which will be far away from the center frequency. So here the moment like that the position of these peaks will be nearer to the center frequency or far away from the center frequency. It is depending upon the K value. So as the K value increases, the bandwidth will be increased. So K value is like 0.001. So the K value, if it is small, so the bandwidth will be small. If the K value increases, the peaks will move far away so that the bandwidth will be increased. The same thing, we'll do the simulation and we'll see that practically is it the same thing happening over here, right? K value it is like a 0.001. 1 milli is nothing but 0.001, right? And the stop value is around 0.1. So now the same AC sweep analysis I am trying to do it here, and output. So previously we did the simulation for that output one for the first circuit. Now remove it, and I am trying to do the simulation for the output 2 for the second circuit, and let run. Yes. So if that scale is too large, instead of taking a linear graph, what I do is I give double click on the scale y-axis, and instead of a scale in linear, I will be converting into the decibel. If that graph is visible, you need not to go. But if the graph is not visible, if that scale is too large, I have to convert into the decibel. If it is done so, 100 units will be converted into the 40 units. So 20 log of 100 is nothing but 40. So that is how I can make that a scale too small if it is like already big. If like the scale is too large, I can make it small. So now converting from the linear to the decibel and give it OK. So this is how that I can see the different waveforms over here. So now what happening, so at initially 0.1 is the K and another one is 0.001 is the K, right? So now let me untick this one, sorry, not this one, untick this one, so we can see that this is what the frequency response for the K value is 0.1. K value is 0.1, sorry, K value is 0.001. As we know the K value is small, it is loosely coupled, and the frequency response bandwidth is very small. So this is how like we can get the frequency response curve. So as it is mentioned, the frequency response curve is this one when we go with the loose coupled. Means like the k value is very small. So this is the k value is very small case. K value is very small case. So now if I untick this one, and if I give that click on this one, if you give this one, so I will be getting two peaks will be located. One is at left, another one is right. From the center frequency, 159 kilohertz is the center frequency. 159 kilohertz to one is like after 159 kilohertz below before that one case. So like it will be somewhat wider than the previous case. So this is how like I can get that more bandwidth if I increase the k value. So as k values increases, the bandwidth will be increased. So that is how like for the loose coupled k value small, I got this curve, and k value if it is maximum, that I got this kind of two peaks. So now I do the same analysis here. I have two cases. So this is the k value small case. This is the k value large case. So I can show you another simulation also. So instead of like two peaks, I'm trying to show you the three peaks. So like I will be doing that simulation for the 3 times by increasing the 45. So here from 1 milli to 100 milli with the step of like around 50. So 1 milli, 50 milli, 100 milli, like that it will be doing the simulation for the 3 times. So run. Yes, remove this one, delete. And that graphs are not visible because of long scale. I select the scale. I'll select the scale, and I will convert into decibels and give it OK. Yes. So here you can see that this is the first peak, and this is the response when we keep it a k value is too small, right? So it is nothing but a loose coupled double tuned amplifier. This is the case where at a 50 milli. So this is the case at a 50 milli. It is somewhat tight coupled, and it is like a very tight coupled when you keep like the k value 0.1. So we will be getting the frequency. It's like far away from the center frequency. So if you keep on increasing the k value, the peaks will be appeared over here, which is away from the center frequency. That is how like we get a maximum bandwidth as we increase the k value in the double tuned amplifier. So now we'll go with the third case. In the third case, so the similar kind of first circuit connected for the 2 times. So this is the single tuned amplifier, this is another single tuned amplifier, and which is connected with the output. That same circuit is connected for the 2 times, that's it, nothing new. So we call this one as a Stagger tuned amplifier. And now what I do is I will be going with the simulation for the third case also, and all 3 circuit simulation means like all 3 outputs. Let me show it on one graph. So for that I will be going directly with the AC sweep. I'm not doing any kind of parameter sweep because I'm not involving any parameter here. So straight away I will be putting like a 3 graphs on one frequency response. As we know, yes, so center frequency is around 159 kilohertz, right? So that's why like I will be keeping center frequency is nothing but this one. So center frequency is nothing but this one, 159 kilohertz. I'm not keeping the inductance value 3 and 5. I'm keeping that inductance value is 1 milli for all the 3 cases. 1 milli here and 1 milli here and 1 milli here. In everywhere, like I will be keeping 1 milli. The capacitance value also 0.001 micro. So it gives like a 159 kilohertz for every case. So now we'll see that 159 kilohertz is required. So like start frequency is at 80 kilohertz and the stop frequency is at 200 kilohertz. I'm putting a linear scale and number of points I'm keeping as maximum as possible, so that it will be doing the simulation for this many times and I will give that result. It is not a mandatory thing, that is your wish. We can change the value, right? So to get like an accurate graph, more linear graph is required, you put like maximum points, right? I will be keeping these many points. And coming to the output, I wanted to see that 3 outputs, output 1, output 2, output 3 I will be selecting, and let me run. I will be selecting three outputs, and let me run. The phase plot, I'm not analyzing the phase plot, so I can delete the phase plot. You select this one, keep the cursor on this one and select this one, and use the delete option. So right. So output 1, output 2, output 3, these three plots we can see it here, but it's not visible properly. It means the scale is too large, so I have to give double click on the scale, right? And here instead of linear I have to convert it to the decimals. Give it OK. So this is how I can see that. So this is the curve, like output 1. So output 1, this is the output 1 curve, right? Output 1 curve, right? And this one is the output 2 curve. Red color is the output 2 curve, and this one blue is the third curve, right? So once I compare the three curves, so this is the single tuned amplifier frequency response, this is the double tuned amplifier frequency response, and this is the staggered tuned frequency response. So with respect to single tuned amplifier, a staggered tuned amplifier gain will be more, and with respect to single tuned amplifier, a double tuned amplifier will be having two frequency response, like it will be at two different frequencies, so like wide frequency range. So that is how I can observe, like so the frequency response for the single tuned amplifier and a double tuned amplifier and a staggered tuned amplifier, so through the multisim.